And let's go to the whiteboard. Let's begin with the most basic version. If I had 2 nodes, this had value 1. It should be pretty clear what number I should put in this box. If I want to maximize the flow, that's pretty easy. Let's make this a little more complicated. What number do I put in here? Well, 1 thing goes into this node, so 1 thing should come out. Now, ask yourself, is this still a maximum flow? Well, this one isn't being filled up all the way, but notice it can't, because in order to make more flow go across, this would have to be bigger than 1, but I can't. So that is the maximum flow. What if I started doing, I don't know, something like added this. Let's say I want to keep this flow maximal. Well, if I put a little 1 here, and then a little 1 here, now 2 come in, and I can go ahead and I could say, put a little 2 there. So now the maximum flow is 2. Notice though that if I change these numbers, if I made them bigger, let's say this wasn't 1, let's say this wasn't 1, let's say this was 5. It's still the maximum flow because I can't have any more come over here. So let's think about this. There's sort of this idea that you might be thinking about paths. So we can think about, okay, it seems like this number is really important, but why is it important? Does it have to be important? Let's add another arc. Let's say this one, I don't know, arbitrarily is 4. Well, we would like to put 4 here, but can we? Well, in order to have 4 there, we need to get 4 more flow, but we can't. This can go to 5, and well, that can be 4. There's something here. There's some combination of how everything's working that is useful, but maybe it's just not quite clear yet. But let's think back to the idea of flows being made up of lines, of paths through the network. So I have this path, I have this path, I have this path, and then I have this path. And let's say my source is right here and my sink is right here. You might notice that I've never really drawn arcs going into the source or out of the sink, and that's because they're really not useful. But let's think about how we would want to construct a maximum flow for something like this. Well, let's think about this. Well, first you think, oh, they're right next to each other. Let's take the shortest path. You say, okay, I filled up the shortest path. Now what? There's already another path. That's the first thing you did. There's a path that's length 2. And now you do that. Now notice with this path of length 2, it could be that this one's the one that restricts your flow, or it could be this one. And that determines what 3 paths you have. And let's think about those 3 paths. One of the things we're going to do is we're going to say, let's just ignore all of the arcs that we've already used up. So if we do that, we'll get something that looks kind of like, so these arcs are in all the versions because they haven't been used yet. Now, and we aren't drawing this one because we've already used it up. And now there are 3 ways that this could go. So we could have the situation where both of these arcs are completely full. So that would lead to something like this. So the first case is that both of those arcs were full. The second case is that only that arc got full. And the third case is only this arc got full. Notice that all of them lost at least 1 arc. At least one of these arcs got completely full. So, in each of these cases, what's the next path? Well, we'd like to do a 1 path, but there's no 1 path. Let's see, can we go from 1 to 1? No, we've already used up the only path that does that in all of these. Can we do it in 3? Well, on this one, we can do it in 3. In this one, we can do it in 3. And in this one, we can do it in 3. But we can also do it in 3 with this on that one, and we can do it in 3 with this on that one. Now, let's think about this. If we notice that there's an absolute limit we can see to how much you could do. Notice that right here, if we fill up this this arc right here, then it's clear we have no more paths. We couldn't possibly do it if nothing can lead the source. And over here, same for this one. And on this one, both of those are critical. Notice that no matter what combination of things you do, some of these are gonna get filled up. We can think about, and we're saying, take a moment and think about this. We can fill up this path first, the one that goes around, or you can fill the one that goes across the diagonal first. Imagine that this arrow always went the other way. This arrow always went that way. Don't worry about it. It doesn't affect that step anyway, so just deal with me here. And we could think to ourselves, in order to have it so that no more can go on this arc, we need it to be that at least one of them on these three are filled up, and for this one, at least one of these three is filled up. Notice that if this one is filled up by the first thing, well, obviously we can't get any more flow by doing the second one, and likewise over here. And this one, obviously, is just filled up with that. So what we're getting at is this idea of an algorithm. We do paths of length 1, then paths of length 2 if there are any, paths of length 3, so on and so forth. And eventually we have to have filled up enough. And it should be pretty clear why that this would create a maximum flow. But what is that maximum flow? What I've described is an algorithm for finding a maximum flow. I'll make the actual name of the algorithm appear on screen, but how big is the maximum flow? If you're given a concrete example, you can just use the algorithm. But what if you aren't? If you aren't given a concrete example and you have some kind of network that looks like this, and you've got X, Y, Z, you can't really do the algorithm on this. And there is a way you can catch this in totally symbolic terms. There is a catch though. And to understand that catch, you need to start thinking about something that I was sort of dancing around before, that there are choke points. That there are some kind of thing, if that's full, nothing go across. Let's think about these choke points. Well, obviously, so that's obviously a choke point. So if that's full, nothing can go across. What other ones? Well, if these two are full, nothing can get through, because all the source can do is go to here. And if these two are full, then that's also a choke. Now all these chokes are called cutsets. And a cutset is a set of arc which, if you remove them from the network, couldn't get from source to sink. And the one I showed here are all minimal, cause let's use this cutset here as an example. If I only crossed out that one, flow could still get around. And likewise, if I only crossed off this one, flow could get around. So this one is minimal. There's no more than could do it. You can have non-minimal cutsets just fine. Like that's a non-minimal cutset. They're not very useful because they just increase the number. And if you're thinking about it, you're thinking about, okay, well, if this is a cutset and this is a cutset and this is a cutset, and let's say we have that's A, that's B, that's C, that's D, then you can say, okay, well, it obviously, whatever this max flow value is, let's call it big F. It's got to be at most D, and it also has to be at most A plus C, and it also has to be at most A plus B. I feel like there's a way that makes this easier. O equals the minimum of D, A plus C, A plus B. Note that this network, we could have added a lot more arcs to it. We could have added more nodes. We could really mess that up, right? We could have huge networks. You could have network, doing all these crazy things. And in principle, you can find cutsets. You just look at your nodes and you decide which ones are needed to get from this little green dot over here to this little blue dot. This is not like a real network, but like it's just sort of showing an imaginary, hugely complicated network. There is a problem. In principle, all you're doing is taking the minimum of a bunch of things. In practice, though, huge. For a network like that, the set of even just the minimal cutsets, which are all you really need for this one because any non-minimal cutset is just gonna be like, oh, also the minimum of A plus B plus C. And it's like, cool, but that's obviously going to be bigger than everything else. So you only need to take the minimum of all the minimal cut sets. Only problem is the set of minimal cut sets can be huge. And it gets huge really fast. In fact, let's go ahead and look at an example where the minimal cut set is very, very large. Alright, how are all the minimal cut sets? Well, you need to take one of these three, and one of these three, and one of these three. So you have 3 choices times 3 choices times 3 choices. You have 27 minimal cut sets. And that's for this example. If I just, drop one of these in and maybe one of these, now the numbers of minimal cut sets is way bigger. Now it's greater than 27, like probably a lot. So you can see that this is a problem. This is not something you ever want to calculate, but it does have a few nice properties, and that is, symbolically, it's completely simple. If I had some network where my arcs weren't just numbers, they were variables, or I had x squared plus 2, x cubed minus 3, this one was x to the negative 1, and I don't know, this is a complete not a thing that would happen. Let's throw in a little x times y there. In principle, you can do this. And let's say, a little bit of a spoiler for what's happening next, you wanted to know the value of maximum flow. Well, if you wanted to know the maximum flow of this thing, it would be the minimums of all the cut sets, which are, this is a cut set, and this is a cut set, and this is a cut set. Let's just say that's all of them. There's probably more. You can figure it out. But now what you could do is you could add all those cut sets together and figure out the minimum of them. Remember this. This will be useful later. Alright, so now we've looked at how we get the value of flow, and we maximize that value in 2 different ways. We look at the theoretical way that's generically applicable, and then we look at the practical way, which requires more specific knowledge, but it's not too hard to do. But now we get to the idea of multiple flows on the network, and you can think about this as different items that need to